Okay, everybody, we're going to be talking about the last topic in this particular unit, and it's the structure and properties of solids. And for the purposes of this course, we're going to talk about 4 specific types of solid: ionic, metallic, molecular, and covalent network. Now, each one of these types of solids is going to be different based on what those solids are made up of. Okay, so our first one we'll talk about is ionic crystals. Kind of touched upon this last year in grade 11, but let's just revisit it. Okay, so once again, we're talking about ionic bonds. So for our purposes, we're going to be talking in this situation of a delta En of greater than 1.7. Okay, so for the most part, metal, nonmetals. Okay, and we're going to end up with actual charges, ions being formed. Okay, so we're going to have cations and anions. So let's take a look at the crystal structure because this one is highly ordered. Okay, and it's highly ordered. So you're going to see an alternating order, because if it isn't alternating between positives and negatives, we're going to get repulsion. So let's take a look here. My chlorine is the green, my chloride ion. My sodium ion is purple. So if we take a look here, negative, positive, negative, and then directly adjacent to that anion would be a cation, and then negative and positive, and so on and so forth. You can predict it, okay, because they're constantly being alternated with opposite charges. Okay, so for that reason, so we've talked about this, for that reason, these ionic crystals, when they are dissolved in water, so they need to be aqueous. So don't forget, when we talk about solid sodium chloride, and when we put it in water, we will end up with aqueous sodium ion plus aqueous chloride ion, right? So these guys will separate. So there's like a little, and for that purpose, we will see that electrons will jump. So my electrons will come here, be repelled, be attracted, be repelled, be attracted. And because they're separated, like in the crystal form, it's neutral. But once they're separated, my electrons will be repelled, or I'm sorry, in this case, attracted, then repelled, and so on and so forth. So once again, just make sure that you're talking about a dissolved ionic crystal, not the actual crystal itself. Okay? They're hard but brittle. And what that means is they will shatter. Okay? And that's because they are so ordered. Because they're ordered, if you put a force on any one of these vertices, you can actually shift. So imagine shifting this vertex or this negative charge here, and then everything starts repelling. And then that's how you've got instability in the crystal. Okay? They have a high melting and boiling point because we're talking about an ionic bond. And we know ionic bonds are very strong. We're not talking intermolecular forces here. We're talking actual covalent or ionic bonds, super strong. Okay? So, summary, the properties are explained by the 3-dimensional arrangement of our cations and anions that are held together in a specific order. And not only are they held together in a specific order, but that interaction, because we're talking about, like electrostatic attraction, makes them really strong and really hard to break. Okay? All right, so that's your ionic crystal. I have a little summary chart right here. Oh, no, I don't. Lies. My next summary chart, or my next type of solid, is the metallic crystal. So these are our metallic elements. And they are held together, first off, by electrostatic interactions and free-moving electrons. So let's think about this. My electrons are free. Okay, they have no rhyme nor reason. They're not, and as we now know from this specific unit, they're not following a path. They are not held to a specific place. Their strength is in numbers. Okay, so not every metallic crystal behaves the same way. And we know this. This is why we choose different metals for different functions. So for instance, we wouldn't use aluminum as a jewel, okay, for jewelry. It's not a jewel, as a base for jewelry, because it is reactive. It's far more reactive than something like gold, okay? Once again, for metals, their properties change because their structure is different. So they can have really low melting points and really high melting points. One thing that doesn't tend to change from a metal, though, if you're talking about a metal of some sort, they are all shiny. They all have, well, I won't say all, the vast majority of them are a silver color, and they're flexible. So we can say that they're grade 9 time, ductile, malleable. Okay, we can change their shape. Okay, also they can conduct electricity and they can conduct heat, and we'll explain why that happens because of a theory, and this is an important one, all right? Importante. It's the electron C theory. So I'm just going to scooch this up. Okay, so what do metallic crystals or what do metals look like? Well, they look like, so pretty much they're very dense, they're tightly packed, and the electrons are free to kind of move around. So it's like loo, you know, they're moving wherever they want, no rhyme nor reason. Okay, because remember, we can predict where they're probably not going to be, and we can predict where they were, but we don't really know where they're going. And we certainly don't know where they are at that moment in time. Okay, so when we talk about the electron C theory, we're talking about the fact that these electrons are not owned by a particular nucleus. Okay, they're constantly moving around. It's like, you know, it's a collective arrangement of electrons. Like it's, you know, that metal owns all the electrons, but each atom's nucleus does not possess or have rights to those electrons. Okay, so that's what the electron C theory means, is that these electrons are moving around just like waves in the sea. Okay, they can't go off into the abyss because there still are nuclei holding them to a certain area. Okay, but they don't have to stick around their own nucleus. Okay, so moving on with that, let's talk about the properties of metals and why this electron C theory can explain. So for instance, they are shiny and silvery because those valence electrons, so the electrons in the outermost energy level, can absorb energy. So they absorb that energy, and remember that makes them into an excited state, right? And then we know that electrons can't stay in that excited state forever. So then they've got to actually come down to ground state. And for that reason, they release the energy. And in releasing that energy in the form of light, that's what makes these metals appear shiny. Okay? Or lustrous, or yeah, so that's a good word. Flexible. Now, we know we can bend metals, we can make metals take different shapes, like I said, ductile and malleable. It's because those electrons are not in like stuck to one place. So non-directional bonds, because it's kind of a fluid electron C, means my metal isn't rigid like a crystal. Okay, so there's still like the nuclei are holding the glue, holding everything kind of together, but those electrons have a lot of movement. Electrical conductivity, remember, when we're talking about electrical conductivity, we're talking about the movement of electrons. So these electrons can freely move throughout a metal because of the C. So the fact that they can freely move, that's electrical current. They're hard because there's a lot of additive strong bonding. Okay, so you have it's still negative and positive charges holding things together. So the fact of sheer number of negatives, those electrons moving in the C, and positively charged nuclei, that's what makes it strong. And it's crystalline because there's still a dense center, and those electrons are still stuck with the nucleus. They're not allowed to just go off. All right. So those are important properties of the metals. Okay. And here's another take on it. 2 different textbooks. Okay. Next, number 3, molecular crystals. Okay. So when I talk about a molecular crystal, these would be between 2 nonmetals. Okay, most of the time. So don't forget, we're talking delta En of between like 0 and 1.69999, right? So there's no ionic bond. These would be our covalent bonds. Okay? So we'll say covalent, whether they be polar covalent or non-polar covalent, we're sharing electrons here. Okay, so when these crystals are in the solid state, they still have an actual repeated structure though. So that's why we can say they're a crystal lattice. There's a repeated structure. They're often a little more complicated because they're not as ordered. Okay, because you don't have that plus minus ordering things, you can actually induce a dipole and change the crystal shape. So they are a little more complicated. So if we take a look at the properties of these molecular crystals, they have low melting points because of the intermolecular interactions, right? There's no ionic bond. So the thing holding these guys together are intermolecular forces. Okay, so much weaker than my ionic bond or my covalent bond. Okay, and that's what I just wrote here. Forces are not very strong compared to ionic and covalent bonds, which explains why it doesn't take as much energy to melt. Okay, and they're not necessarily as hard because they're not as ordered. Individual particles are neutral, and they do not conduct electric current because there's no ions or no positives and negatives, okay? Even if you melt it, okay, because they're neutral. There's no charge. And lastly, the 4th type of solid that we're going to talk about today, near and dear to my heart, you'll see why in a minute, the covalent network crystals. Okay, these are solids once again, and we've got covalent bonds. Okay, so there's still sharing of electrons, but they're really complicated, okay, because they build upon each other. And what we can say here is because they build upon each other, we can say that there's strength and a lot of strength in numbers. Okay, so for instance, a common element that's central to our covalent network crystal is carbon. And we've been playing a lot with carbon, and we know carbon makes 4 bonds, 4 equal covalent bonds. Okay, so we know because we promoted that 1s electron, we've got sp3 hybrid orbitals. So we know it's a tetrahedral shape. Okay, it's a tetrahedral shape, and it keeps adding to each other, and you'll see that diagram in a minute. So because there's those strengths in numbers, you still have a covalent interaction. And remember, covalent bonds, not as strong as ionic bonds, but way stronger than the intermolecular forces. They've still got a high amount of strength. Okay, so these guys, because there's so many of those bonds, and we're talking about building upon different actual molecules, you've got much strength in numbers, and for that reason, they've got super high melting points, and they're extremely hard because of all the bonds involved. Notice how I'm not saying forces, I'm saying bonds. So there's no flexibility, okay? There's no movement. It's not like an electron C, and you can't induce a dipole. So these crystals are pretty stuck in place, okay? So for that reason, once again, they are hard, but if you force the crystal to readjust, they will shatter, okay? They're insoluble in water because they are not polar. And because there's no ions, they don't conduct electricity. Okay, so here's some good pictures. And I'm going to attach another PDF that I found that will show you as well. So here's the reason why I love it so much, diamonds. So remember, we know that diamonds are made of carbon completely. Diamonds are carbon that is sp3 hybridized. Okay. We've got the buckyball, we've got graphite now. Graphite is linear, so graphite is more sp hybridized. Okay, and we've got nanotubes, so this is for our nanotechnology. So very strong, inert, doesn't conduct electricity. There's a lot of good qualities about these covalent network crystals that make them in high demand. There's actually another one. If you want to do a little bit of reading, you can look up graphene. This is a new carbon-based substance that is being used in nanotechnology now. Okay, it's like 1 atom thick covalent network crystal. So there's a lot of new technology-based reasons why they would want to make graphene. So take a look at that. It's kind of interesting. Okay. Last little section, semiconductors. They consist of our covalent crystals. So once again, silicon, germanium, we're talking group 4 elements that conduct a small amount of electric current. So a bit different from our covalent network crystals. They can conduct a small amount of electric current. And like at room temperature, so remember SATP, standard conditions. If you heat them up slightly, you can actually cause electrical conductivity to increase dramatically, all right? So they can dope these semiconductors with boron or arsenic, which we know are away from our group 4 elements, and that allows the engineers to change the properties of these conductors, and they now can, once you dope them with those elements, they can create something called a superconductor. Okay, these are the functions of these conductors and superconductors are in all of our electronic devices. So it's something that is really relevant today, and even more relevant now because that's all I feel like I'm connected to these days is an electronic device. So lastly, you can take a look at this particular figure and read through it, and I will highlight this homework section. And I want you guys to know we're missing you. And if you have any further questions about this section, please put those questions in your discussion Dropbox, which is found in the class tools. You take care, and you'll hear from us